Good afternoon, everyone. My name is Roger Lin, and I'm from the UCSD Summer Research Program. And today, I'm here to share with you my project, Shut-Up Clones, Simulation of Multi-Layer Agent-Based Models. And before we delve into the details of the project, here's two key concepts I'd like to share that forms the foundation of the project. And understanding these concepts is going to help you understand the significance of our approach and findings. So we'll first talk about agent-based model, and then we'll move on to multi-layer networks. So what is the agent-based model? The agent-based model, also known as ABMs, focus on individual entities known as agents. These could be people, animal, or even bacteria. And by adjusting agent parameters or behavior, we then observe how they interact with each other or the environment in order to find a bigger pattern in the system. So over here, we have a virus spread example where we can set the agent parameters over here, and then we move on to observing simulations and trying to find a bigger pattern. Since the probability of recovery and gaining resistance are both set to 0%, we expect to see the entire network being infected over time. And indeed, that's what we observe over here, where over time, 100% of the nodes are infected. And agent-based model simulation could also be used in a lot of other areas, including population prediction and rumor spreading, which we're going to talk about later. So after we understand what is the agent-based model, what is a multi-layer network? As some of you might recognize, this is the old Facebook login page. And this is a good representation of what a social network is, where we have nodes that represent users' account, and also edges that represents connection or relationship. Now, as humans, our lives are made up of different aspects, including work, family, or even your Christian fellowship group. And all these unique networks has their own characteristic, including interaction frequency, and nature of interaction, and even the people involved. So this might be a workplace network, and this might be a family network. Notice how the edge structures are a little different, because one is more likely to know the most member in their family, but not necessarily in a company. And here's two things to keep in mind here, that the nodes on the same vertical are considered the same person. I like to think of them as clones because they're essentially representing the same person on a different context. And also, the nodes in each layer without connections, this simply just means that they're not currently part of the network and does not have an impact over the network. An easy way to understand this would be assuming that different layers are representing different social platforms, where some people might have both accounts, some might have none, and some might only have one of them. It's always okay to sign up for an account later, but until then, they would not have an impact on the network nor connections. So now that we also traditionally agent-based model are run in a single layer. This ignores the multi-identity of a human and misses to capture an important characteristic in social interaction. So now that we understand that a multi-layer agent-based model provides more accurate result, why is this important? Why do we care about this? So in 2020, COVID-19 became a global health crisis, and as vaccines are being rolled out and developed and rolled out, misinformation spread rapidly online. And this report, titled Disinformation Dozen, published by the CCDH, Center for Countering Digital Hate, reveals that 12 individuals were responsible for 65%, nearly 2/3 of anti-vaccine content shared or posted on Twitter and Facebook across the span of February 2021 to March 2021. That's over 500,000 anti-vaccine content posted or shared in just 45 days. And another study suggested that an estimate of 200,000 preventable deaths due to unvaccinated adults from the span of June 2021 to September 2022. That's 200,000 lives in just 15 months, which largely could have been preventable by getting vaccinated. So these findings suggested that the influence of social networks and how a few key individuals can impact the whole network. And by identifying and understanding these key individuals, we're able to counter misinformation, and which is important in protecting our society and democracy. So the simulation tool that built can do just that. And here's the example. So over here, we have 30 nodes with 15 nodes on each layer, with layer 1 representing Instagram and layer 2 representing Facebook. Now the question is, which node represents the most which node is the most significant across this network? And we see this node with the highest degree of centrality in layer 1, which means that they have the most connections on Instagram. And also this node having the highest degree of centrality in layer 2, which means they have the most connection in Facebook. Now the question is, which of this node has the most influence across the entire network? Let's find out. So after we define our social network, we're now ready to build our own agent-based model, following the procedure we mentioned earlier, with agent attribute, simulation, and finding pattern. The only differences here is that this model is built in Python, so it provides us more flexibility to use the tool that I built to run multi-layer simulations. Let's go through each of them in detail. So over here, we have agent attribute, where we have 15 nodes, as mentioned earlier, 15 nodes on each layer, representing 15 individuals, and there's 49 ticks or rounds. At each tick, we'll record the total rumor spread, and then compare them to find out who's more influential. And initial rumor count, which is always set to 1, and seed, which defines the initial rumor spreader. And this allows us to compare different seeds to find out who's more influential. As this is a more simple agent-based model, there's only one agent parameter, which is rumor probability, that's set to 2%. What this means is that at each tick, agents, when receive the rumor, is going to check their neighbor, and if their neighbor has not received rumor, there's a 2% chance that they will. So now we're ready for simulation. As we can see here, we see the rumor at this node over here, which is the node with the highest degree of centrality in layer 2. And we can see the node being light up, showing that they have received the rumor. And after this, we're ready for even more simulations. This simulation is actually run 1,500 times, 100 times on each seed, which is from person 1 to person 15. This reduces randomness and allows us to correctly identify the pattern. So now we're ready to look at the plot. Here we see the average rumor count as the y-axis, and for x-axis we have the tick of time. We see many nodes with different ranges. Let's clear up the plot a little to keep the 3 most influential nodes. So here we have it. This person, we see that this person has a notably dominant spreading process, spreading the rumor faster and more widely than anyone else. And this node is actually neither the node with the highest degree centrality in layer 1, nor the one with the highest degree centrality in layer 2. But it's actually this node that has a more average connection across both layers. And we wouldn't be able to identify this if we were to run the simulation in a more traditional way, where we look at the network separately. So using our multi-layer simulation tool, we're able to identify this node that allows us to identify the most significant node, and by either educating these key individuals or trying to slow down the spreading process, we're able to counter misinformation. And this simulation tool could also be used in a lot of other cases, including population spread, population dynamics, and understanding social networks. So what's next? Our multi-layer tool plays a crucial role in identifying nodes for countering misinformation. And the recent incident shows the urgency and seriousness of this topic. Roughly 2 weeks ago, there was a knife attack at Southport, England, which claims the life of 3 young girls. And hours after the attack, there was a rumor claiming that the suspect was an illegal immigrant, which sparked anti-immigrant protests all over United Kingdom. And this eventually became the worst UK riots in 13 years. That is still currently ongoing. So this shows how misinformation can escalate into societal consequences and causing being a threat to democracy and public safety. So our goal is to lower technical difficulties for running simulations so more people could focus on finding the pattern in our society and making it a better place. And as the US presidential election is around the corner, there's going to be more discussions online along with more misinformation. So I would like to invite everyone here to pause, think, and check before we share any content online, because this is what we found. If the most significant node that we just identified did not help spread rumor within the network, we see a 35% decrease on average for rumor spread at tick 49. So set your misinformation resistance to max, and let's fight against misinformation together. And here are some references for my project and slides. And I also like to acknowledge Professor Nakizade for mentoring me. And thank you all for listening and being here today. Thank you. I am happy to answer any questions.
This is just out of curiosity, like how fast do these AE simulations run? Like are they slow or?
So we have the ticks and rounds, that's like 49. So it's kind of like a simulation timing. So the simulation can run really fast. 1500 time of simulation can probably run in like a few seconds. So yeah.
Okay.
Yeah.
So I'm kind of interested. I feel that in real life, the different social networks would be highly correlated. Is there really, did you notice a significant performance improvement in using multi-layer networks versus just a single one?
Yeah, so that's a very good question. We have different network because, for example, there might be different algorithms on different platforms, which could cause the difference. And also, I don't know about you guys, but a lot of more younger people, younger generation uses Instagram more than Facebook. This would also make a frequency difference when you're doing simulations, where you can like adjust the weight to make a network more influential in the simulation. So there will be a difference there to provide more flexibility in the simulation process. Yeah. Over there.
Based on your testing and simulation, do you think creating some form of hierarchy within the layers of your network could affect the results or contribute to like more accurate?
What do you mean by hierarchy?
So essentially, like in the case of the rumors, essentially like formulating one layer of the network to be a lot more prone to providing you rumors in another layer, and just seeing whether one would lead to the other, or you know.
Yeah. So there's like a function called cross-posting, which is like when you post an Instagram post, it might also post on Facebook, and that would be like a great example of like a hierarchy network. And this is more specific to cases where it could be done in the multi-layer tool, and we can like adjust how the simulation should be done. And it is a great way to fit to different cases. So yeah, it would be a good usage of the tool. Yeah.
Also, I have some confusion over the multi-layer model.
Mm-hmm.
So how is it different from a flat one layer?
Yeah. So is there anything?
One is spatial and one is intern, but what if we just treat it as functionless?
Mm-hmm. That's a really good question that I also had when I was doing this project. And as mentioned earlier, since different aspects or different layers and different environment has a different characteristic, like frequency we talked about, people involved we talked about. So without like specifying which group of people belongs to which simulation process, we're going to have less accurate simulation. So to answer your question, like I mentioned earlier, Facebook and Instagram might have a little different usage frequency, and in order to make that in the simulation, we'll have to like separate them into like two different layers of network in order to provide more accurate results.
Talk a little bit about the scalability of this. So like, what's the like largest network you try, and how do they perform computationally?
Yeah. So the library that I'm using is called Repass for Python, and it is developed with multi-core processing, which is used for really large computation. But currently, I'm running the simulation on my laptop, and the furthest I've done is like 100 nodes with like 100 tick of time. That is like somewhat the limit because the larger it gets, because we have to store all these receipt rumor as Boolean values in the matrix to record which time frames are they receiving the rumor. So once the network becomes too big, the matrix also becomes a lot bigger. So that would be like the bottleneck for running simulation on like this kind of device. Yeah. Any other questions? If not, thank you and have a great rest of your day.